Now, in a few moments, we're going to actually prove that this type of framework is exactly mathematically equivalent to solving the wave equation. But to think a little bit about what this is really telling us, let's think about a little scenario that we might want to consider. We could consider the following. It's a little bit of a science fiction scenario, but I find it particularly fun to think about. Let's suppose, for example, we were interested in the orbit of the moon around the Earth. Or say, actually, some aliens from outside our solar system are interested in this type of a thing. So here's our Earth, and I'm trying to draw some kind of, North and South America type of a thing. I'm not really a great artist, but, something like so. And then I've got my moon, say, that's in orbit around the Earth with one of its big craters up here. And let's say these aliens have come into our system, right, and they're observing what's going on, and they know everything, that they need to know to calculate the moon's orbit in, say, the year 1900. Then they fly away. And while they're away, they're interested in knowing where the moon is going to be, say, in the year 2018, at a very particular, say, instant in time. And so then, if they carry out this quantum mechanical calculation, which is then going to give them a certain probability distribution of different outcomes, maybe of different locations of where the center of the moon is going to end up after that period of time. If they want to carry out a proper calculation, what this sum over histories approach says is that they have to consider then all possible histories and events leading up to this final location of the moon. And in particular, they have to consider all things that would be relevant to affecting the moon's motion. Now, of course, the moon is a very massive object. We'd be talking about a very narrow probability distribution, fundamentally, with a very small de Broglie wavelength, but we're just thinking right now about matters of principle. And while we're thinking about matters of principle, one of the things that in principle at least affects the moon's orbit is the gravitational interaction with the Earth, which depends very slightly, but we are talking about matters of principle, on the distribution of mass on the surface of the Earth. And if these aliens, right, are going to do a proper calculation and of what their observation will be when they come back, they have to consider all possible arrangements of mass on the Earth's surface, or they will not get the correct distribution. Now, some of these distributions on the mass throughout time between 1900 and 2018 correspond to some very interesting scenarios. Right? For example, there would be a particular scenario of distribution on the mass of the mass on the surface of the Earth during this time frame. If, for example, the Nazis had won World War II, right? That's a scenario that has to be included in this sum over histories, or they will not get the right distribution. Likewise, perhaps there's another scenario where the Soviets win the Cold War. Or maybe in the Cuban Missile Crisis, humanity goes over the deep end and annihilates itself in a big nuclear holocaust. All of these scenarios have to be included. So in some sense, they are out there. In some sense, there's some kind of reality to all of these alternate histories. If you want somewhat of a less science fiction-y type scenario, actually the whole premise behind quantum computing and the excitement here all comes from this sum over alternate histories type of an approach. One of the biggest applications for quantum computing is decryption, right? Undoing encrypted digital data. Right. And that type of decryption depends critically on factoring a very large composite number that's the product of two very large unknown primes. And that's computationally a very difficult problem to solve, and that's why these encryption keys work so well, but that's also why there's so much interest in cracking them. And the way a quantum computer can do this in a very short period of time is that when the quantum computer is testing out all the different possible prime factors, one of the beauties of the process is that it can actually do all of the divisions of all of the different numbers as different alternate histories and get to the answer instantly. And well, not instantly, but after just one main computational step, because it's dividing by all possible numbers as it goes through all of its different possible histories. Now, this does sound kind of science fiction-y, so let's take a look at a real application right? That where we know the answer in a familiar context and prove to you that this approach is in fact mathematically equivalent to the wave equation approach that you've already learned to apply.